Hello, in this talk I want to discuss the role of dependent sources in Thevenin and Norton equivalent networks. Now, we haven't really talked much about dependent sources so far, so I'll start off with a definition of what I mean by a dependent source. A dependent source, and we normally draw them in diamond shapes rather than the usual circles for independent voltage or current sources, is a voltage or current source whose value is not fixed, but which is dependent on the current or voltage somewhere else in the network. So, for example, I could have a voltage source here connected to a resistor, and I could consider that that is my two-terminal network. But the voltage source is not a fixed value of volts, it is dependent on the current through this resistor. Now, provided it's linearly dependent on the current through the resistor, in other words, it's some constant factor times the current through the resistor, then the whole circuit is still linear. Double all the independent sources, the currents will double, the value of the dependent sources will double as well, everything will double, and that is one of the requirements for a linear circuit. So take an example here. Supposing this is a 1K resistor, the current flowing through it is I, and the value of this dependent source is 500 times I. So it is linearly related to the current. What would the Thevenin equivalent network of this network be? Well, what we can't do is set all our voltage sources to 0 and then just consider the resistance between the two terminals in order to work out the Thevenin equivalent resistance. If we did that, in this case, we would set our voltage source to 0. We would think that the Thevenin equivalent resistance between A and B was 1K, 1000 ohms. But it's not. And the reason that doesn't work in this case is because we have a dependent source. That technique of setting all of the independent sources to 0 and then just looking at the resistances only works if you've got independent sources everywhere. With the dependent source, we have to go back to the original method of determining the Thevenin voltage source and resistance. And that means, what is the open circuit voltage and what is the short circuit current? Well, the open circuit voltage is the voltage between A and B when there's nothing connected to the network at all. If there's nothing connected to the network at all, then there will be no current. If there's no current, then this voltage source will have no value. This will be a 0 voltage source. And if this is 0 volts, then the open circuit voltage will be 0 volts as well. So VOC will just be 0. Now, the short circuit current. The current that would flow in this network, if I connected A to B directly, I can determine by applying Ohm's law to this resistor. The voltage across the resistor would be the voltage coming from this dependent voltage source, which would be 500 times I. And in this case, this is ISC, the short circuit current, because the current flowing through this resistor would be the short circuit current. And that is equal to the current through the resistor, ISC, times the value of the resistor, 1K. And now you can see that we've got a problem. The only solution to this is that the short circuit current is 0. But if the short circuit current is 0, then we can't work out the Thevenin equivalent resistance. Because the Thevenin equivalent resistance is the open circuit voltage divided by the short circuit current, and that would require me to divide 0 by 0, and I can't. So how do I work out the Thevenin equivalent resistance for the circuit in this case? Well, I'd have to do it by finding another data point. Not the open circuit voltage, not the short circuit current, but something else. And a common way to do it is to put a current source on the two terminals. So let's supposing I have a 1 milliamp current source and I feed it in like this. I put that between A and B. Now I'm trying to analyze this circuit. I have a voltage source here, a dependent voltage source of 500 times the current flowing. I have a resistance of 1K, and I have a current flowing. I'm defining what the current is. It's 1 milliamp. Now, the way I've done this, it's 1 milliamp flowing in this direction, which is 1 milliamp flowing through the resistor in this direction, which is going to mean that the voltage here is 500 times minus 1 milliamp, because this voltage source was 500 times the current flowing from left to right through this resistor. So the voltage source here would now have a voltage across it of minus 0.5 volts, 500 times 1 milliamp. So let's define this point down here as being my local ground at 0 volts. The voltage here would be minus 0.5 volts. The current flowing through this resistor here is 1 milliamp, which means the voltage across this resistor would be 1 volt. 1 milliamp times 1K. The voltage across this resistor is 1 volt. And on this side, it's minus 0.5 volts. On this side, it must be plus 0.5 volts, so that the voltage drops by 1 volt across this resistor. So I've determined a point that the voltage across my two-terminal network is 0.5 volts when there's 1 milliamp flowing into it. I know that the Thevenin equivalent voltage is 0 because my open circuit voltage was 0. So my Thevenin equivalent network for this network is just a single resistor. And I now know that if there's 1 milliamp flowing through this resistor, then I will get 0.5 volts across the resistor, across my equivalent network. From there to there is 0.5 volts. That would be true for my equivalent network here as well. So the value of this resistor, my Thevenin equivalent resistance, will just be the resistor for which 1 milliamp flowing through it produces a potential difference of 0.5 volts. 0.5 equals 1 milliamp times RTH, just Ohm's law again, which gives me RTH equals 500 ohms. So the Thevenin equivalent resistance for this network is 500 ohms. And this is not obvious from the value of the 1K resistor in the network, and you can't derive it from just looking at the open circuit voltage and the short circuit current. Does it work? Once again, we can have a look on the simulator. This is how you draw dependent sources in the simulator. It's a voltage source from here to here, but it's a function of the current flowing through this ammeter that's part of the component as well. So this is a voltage source which produces a voltage between here and here equal to 500 ohms times the current flowing through this ammeter here. Now, its open circuit voltage, which I'm measuring at the moment, you can see is 0 volts. If this really was equivalent to a 500 ohm resistor, then if I put 1 milliamp flowing into it, I should get 500 millivolts across it. Let's try. Yes, I do. And if I put 2 milliamps into it, I get 1 volt. And if I put 10 milliamps into it, I'll get 5 volts. It's behaving exactly like a 500 ohm resistor. The voltage across it is proportional to the current flowing through it, and the constant of proportionality is the resistance 500 ohms. I won't talk a lot in detail about dependent currents and dependent voltage sources yet. We'll return to them later on in the module. For now, I just wanted to warn you to take care if you're trying to develop a Thevenin equivalent network for anything with a dependent source in it. That's almost the end of these talks. One more to go, in which we'll have a look at an outline proof of Thevenin's theorem.